One. Okay, so today we're going to be looking at section 7, the density theorem extended. So this is one of the most difficult sections in the paper. And in this section, we're going to use the stuff that we've been working on in the earlier parts. So what did we do in the earlier parts? Well, we got the complex analysis to get the explicit formula. We did small support. And then in section 6, we developed some expansions of Bessel and Kloosterman sums to get us to the point where we now had interesting quantities to calculate. And the first thing we did is we said, let's just use trivial estimates everywhere and see what that gives us. And you have to remember that the quantities that they're doing here do not necessarily have a division by the number of elements in the family. And once you divide it by the number of elements in the family, if the support is sufficiently small, nothing contributes. One of the reasons nothing contributes is when we looked at the sum over primes coming from the explicit formula, it was really a sum not just of primes, but prime powers. And we could trivially bound the contributions from the third and higher powers. And for the prime squareds, we actually rewrote it and we pulled out the main term, or what looked like a main term from that. And what was left over doesn't contribute for small support. All right, so now we're looking in section 7, and we're going to proceed with the asymptotic evaluation of the P star and the P sharp. So the first thing is that some of the terms can be absorbed by other terms just based on their size. And so you always have to keep track of how large things are and how big is your error. If your error term is of size n to the 3/4, should you care about a term of size n to the 1/2?
No.
No, it's going to be absorbed by the error of size n to the 3/4. You could have anything of size n to the 1/2, and it wouldn't be noticeable. So if you've already put in an error somewhere, there is no reason to try to do a calculation in greater detail if it's smaller than that, except if you think that eventually either you can improve your error in that other place so that you might be able to detect this, or that the calculation that you're doing, you might need that independently for something else. So if those are the cases, then you can try to do the calculation in greater detail. Otherwise, there's no need to do this. All right, so now we have all the expressions from before, and we basically say there's no contribution to bk star from the sum over primes. And we get bk star is equal to the following expression. And this works. Somebody is trying to come in. Did somebody just let them in? Excellent.
Yeah.
So bk star, we don't really have to worry about any of the other stuff. We have a very nice answer for it, and it holds as long as v is at most 2 log kn over log k squared n. Well, if you fix the weight k and you let n go to infinity, the log of kn is essentially the log of n. Log of k squared n is essentially the log of n. So this is telling you that if you let weight be fixed and the level go to infinity, you can take support up to 2. And so this is the orthogonal family when we're not splitting by the sign of the functional equation. If, however, you let the weight go to infinity and the level be fixed, then it's much worse. Then you only get support up to 1. And so that's what theorem 7.1 is. So if we don't split by sign, we get up to -2, 2. So now we want to deal with pk sharp. This is going to be the hard term. And this is the term that will contribute if the support is greater than -1, 1. Okay, so what they say is, all right, so now we have equation 7.5. And this is a sum over all L and M. Well, for us, if we choose the special case when n is a prime level and not just square free, that'll make that sum a little bit easier. Or you can say, well, you're in for a penny, in for a pound. It's already so much of a nightmare. We might as well just do it as generally as possible. Then the R's are these Ramanujan sums, and they're just very well-known arithmetic functions. almost anything which Ramanujan is attached to is going to be well studied. You're absolute genius. And he had an incredible intuition for things worth studying. And so we have this, sum over here, which is the arithmetic, and then we have this integral. And that's the integral we need to deal with now. And essentially what we have is we have an integral transform of our function phi hat. So you take your function phi hat, you evaluate it this nightmare, and then you integrate it against a Bessel function. It's going to give you a new function. And this function will be related to your original function phi, or phi hat. So the first thing is, the world is different in many ways from when I went to college. When I went to college, I was a double geek math and physics, and one of my physics professors told us that you should have two table of integrals. You should have a monster table of integrals that you keep at home, and you should have a small portable table of integrals so you always have integration formulas on you 24/7. Why do we not need to have this nowadays in the 21st century?
We have computers.
I'm sorry?
We have computers.
I can't hear you. Could you speak louder?
We have computers.
Yeah, you have computers, you have the internet, you can search and you can find these things. And so for us, it's not as important to have all these tables of integrals. But a lot of people spend a tremendous amount of time over the years constructing these tables of integrals. And these are not just standard polynomials times exponentials. They involve a lot of special functions. And so it is worth knowing about these. Gradstein and Risnik, that's the reference GR, is one of the two most famous ones. The other one is Abramovich and Stegan. These are, I believe, available online, and formula 6561.14. So that just gives you a sense of just how many integration formulas there are in the book if you have something labeled 6.561.14, okay? And it says the integral of the Bessel function against y to the s dy is a nice ratio of gamma functions. And so what they tell us is that, well, we could actually do some integration techniques and play some games, and our integral is the same as now integrating phi log r, evaluated the special point against the ratio of gamma functions. And what's nice is that, well, maybe things are going to be nice as x gets very, very large or x very, very small. Maybe we have a control of what that ratio of the gamma functions look like. Maybe we can expand it. You also have this 2 pi ml over b squared of n to the 4 pi ix. Well, that's essentially some number to the, that's like e to the 4 pi ix log of that quantity. This is kind of looking like a Fourier transform. And that's essentially what's going on here, is we're basically replacing the Fourier transform like this and doing some integration. Now the next part is they are very careful about convergence. And so they introduce a small parameter epsilon. And so chi, I will not publicly state I don't like this notation, but I might say, given that we have Dirichlet characters in other places, it's interesting to use chi over here. And so they'll have, chi of s is this, sum involving Ramanujan functions. When you look at this, there's concern about whether or not it converges. When you put in epsilon as a small positive real number, that's going to give you a little bit more decay. And that will give you enough so that things will converge. And so it turns out you can actually represent this nicely as your products of zeta or partial zeta functions. And so alpha and beta have these nice product representations. And again, none of this is stuff that we will need to do anew for our project. This is why I gave you the lecture earlier where we looked at the 2-level density and the 3-level density, and I showed you we do a nice change of variable and we reduce it to the case that Ivanus Luosanek considered. And so they want some growth rate on chi of s for convergence. And so what they do is they look at the series expansions of these quantities. And they only keep track of the main term and the first lower order term. There's a small chance that one of these was slightly wrong, but not wrong enough in a way that really mattered to us. I will have to double check my notes on this. And so we now get this formula for chi of s, where you have a nice main term, smaller. And so they also use now some properties of the gamma function. Gamma of k plus s over 2 is related to gamma of k minus s over 2 with a couple of other factors. And given that we want to look at a ratio of gamma functions, this is precisely what we want. It allows us to replace the ratio of gamma functions with k over 2 to the s, 1 plus something small. And now our integral becomes a lot nicer. We no longer have those gamma factors. We now have dx over epsilon minus 4 pi ix. And now it's really clear why we want epsilon there. If epsilon was 0, we would be integrating dx divided by x. Well, that blows up at x equals 0, but it's an odd function and we're integrating it against an even function. But now we have the k root n over 4 pi to the 4 pi ix. That's no longer odd. Okay, so it looks like things should be okay, but we want to be a little bit careful. And so the epsilon.
Wait, what is this notation? The sum, just the sum and the integral. What does that mean?
That basically means we're being lazy. And so rather than writing everything out, because if you did, you wouldn't be able to have it fit on one line, they're just saying the sum of the integral that we're looking at is the following.
Okay.
Sometimes what people do, and I often do this, is you introduce new terminology. And you say, let's define this as T of n or U of n or something like that. And the problem is, as you keep doing this, it gets longer and longer and longer. You have more and more things to remember. And this is something that's really not that important. It's only short term. But it is worth thinking about these issues as to how do you want to write things up. And so now, because we have this exponential function, and the exponential is hidden as the k root n over 4 pi to the 4 pi epsilon ix, that's really e to the 4 pi epsilon ix log of crap. That's where the sines and the cosines come into place. And so they just look at what happens, and then they take the limit as epsilon goes to 0. And when you take the limit as epsilon goes to 0, phi is an even function, cosine is even, 4 pi x squared plus 1 is even. So let me see what's going on there. They say that the cosine piece just vanishes. Okay. Okay. So why would the cosine piece vanish as epsilon goes to 0? It doesn't vanish. As epsilon goes to 0, what does the argument of cosine go to?
What?
Yeah, the argument goes to 0, so the cosine goes to 1. And what does the phi term go to as epsilon goes to 0? It just goes to 0. So if you've seen a Cauchy distribution, the Cauchy distribution is 1 over pi, 1 over 1 plus x squared. And that integrates to 1. So this is slightly different than that. We have 1 over 4 pi x squared plus 1. The idea is as epsilon goes to 0, this second integral is essentially just integrating phi of 0 times the cosine of 0 times dx over 4 pi x squared plus 1. And the integral of 4 pi x squared plus 1, I guess, just goes to 1/4. And so that's the second integral. Now we're left with the first integral, integrating phi of x against the sine with a dx over 4 pi x. And before you do any calculations, you always ask, do I need to worry about this? Well, phi is even, sine is odd, 1 over 4 pi x is odd. Okay, so we're integrating an even function, so yes, this could contribute. And so that gives us the integral that we're looking at now. So we've changed things. We've got the choosing r to be k squared over n. And we now have basically the integral of phi of x sine 2 pi x over 2 pi x. And that gets us to the equation on the top of page 101. And it turns out that sine 2 pi x over 2 pi x, this is exactly what you get when you look at the expansions in random matrix theory. And so it is a success to this point. And so now they go through in 7.7 and just say this is the range, in which case things don't really contribute. And that leads us to equation theorem 7.2, that the density conjecture holds up until here. So what was going on here in this section today? We used the Bessel-Klustermann expansion to have a huge arithmetic beast times a nasty integral. But there exist techniques to handle those nasty integrals. In a lot of the calculations we're going to be doing, the whole point is we do a clever change of variable so that we always, always, always reduce back to a Riemann-Sums. I will propose a problem which I have mixed feelings about proposing, but it's worth throwing out there. I applaud myself for being clever and bypassing the need to handle the generalized Bessel-Klustermann challenge by changing variables, changing my test function, and now I can just appeal to the Riemann-Sums result for the one level. This seems like a really good addition. The difficulty, of course, is now I have to do some combinatorics afterwards. And because I have to do the combinatorics afterwards, I have to pay the price. Most of combinatorics is like this. You show two things are equal, and one of them is hopefully computable, and then you get the other. Maybe it would be better not to do this clever change of variable. Maybe it would be better to say, rather than doing the change of variable, which allows you to bypass the Bessel-Klustermann challenge, but it then forces you to do combinatorics later, why not keep things as they are, as a two-dimensional calculation? And then see if you can actually do the generalization of Bessel-Klustermann. And if that's the case, then the combinatorics hopefully would be a lot nicer, and you wouldn't have to worry about all this. So if you're looking for something to try to do, I think it's worth investigating that. Okay, I'm getting my internet connection is unstable, so I want to ask if there are any questions before I stop the recording.
Could you just repeat the last like two sentences because we couldn't hear you very well?
Okay, the last two sentences was a quick proof of the Riemann hypothesis. I don't know if I'll be able to do it again. So there's a joke that the famous analyst G.H. Hardy wrote a letter to somebody saying that he has a proof of the Riemann hypothesis and he will present it when he returns from his trip to Europe. And you know, he's one of the few people back then who legitimately had a proof. And the story is he was terrified of traveling, but figured that because of his reputation and that he could conceivably have had a proof, God would make sure he returned safely. So what I was just saying for the last bit is I have applauded myself for years about being clever and bypassing the need to generalize what Riemann-Sums did for Bessel-Klustermann by doing this change of variables and changing the test function, but that then leads to very painful combinatorics. Maybe it would be better to try to generalize Bessel-Klustermann and not come up with a new test function, but just do things directly. And then you would not have to do the painful combinatorics. There's always choices in life. It's not always clear which way is best. And so it might not be a bad project to just see how bad would it be to try to generalize the Riemann-Sums to do the two-level calculation directly. You know, we've got a lot of people. This would be a great way for you to get a sense of, do you understand the paper? You would not be proving something new. You'd be coming up with a new approach to get an old result. And if you think that this is not valuable, Google Tate's thesis. And a lot of what Tate's thesis was introducing notation and ways to look at things in a new way, which proved very fruitful for decades of number theory. All right, any questions on what we've done? All right, so I will send more details later today. We are now at the point where we've definitely done enough so that we can do some of these calculations.